Let me introduce the following concept. Okay? Consider the differential equation for a gain, which is linear, nth order, homogeneous differential equation, say a sub n of x times nth derivative of y plus a sub n minus 1 of x times n minus 1th derivative of y plus dot 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 a sub 1 of x times y prime plus a sub 0 of x times y, that is equal to 0. Okay? Linear, nth order, variable coefficient, homogeneous differential equation, where I assume that, assume all the coefficients ai of x, they are continuous, on some interval I, and the leading coefficients, a sub n of x, right? A sub n of x is never 0 on the interval I, For this differential equation 4, we call n set of n linearly independent solutions of that differential equation on an interval I. We call it a fundamental set of solutions of differential equation 4 on the interval I. You must note that the order of this differential equation, which is n, it must coincide the number of linearly independent solutions. We should have exactly n linearly independent solutions of that differential equation. Then we call the set y sub I, where I is moving from 1 to the n, to be a fundamental set of solutions of differential equation 4 on this interval. Any such differential equation always has a fundamental set of solutions, as the following theorem shows. Existence of a fundamental set of solutions. Any linear homogeneous differential equation 4, Ly is equal to 0. I hope you remind what is L, L of y. It's the nth order linear differential equation. Always has a fundamental set of solutions on I. It always have a fundamental solution. In proving this theorem, again I am assuming that n is equal to make things simple. And by theorem 4.2, right? That's theorem 4.2. It's a unique existence of solution for initial value problem, right? So by that theorem, choose arbitrary point x0 in the interval I, and consider the following two initial value problems. Differential equations are the same thing. The second order linear homogeneous differential equation. First initial value problem requires the initial condition to be y of x0 is equal to 1, and the y prime of x0 is equal to 0. Second initial value problem requires y of x0 is equal to 0, y prime of x0 is equal to 1. Both this first and the second initial value problems by theorem 4.2, they should have a unique solution, say y sub 1 and y sub 2 on the interval I, right? That is guaranteed by the theorem 4.2, right? For these two solutions, y1 and y2, y1 is a solution to this initial value problem first. Y2 is a solution to the second initial value problem. Compute the Wronskian at point x0. Okay? That's the determinant of this 2 by 2 matrices, right? How much is this one? That is 1. How much is this one? Okay? Because this is a solution to the second problem, that is 0. What is the y1 prime of x0? That is 0 from this initial condition. What is the y2 prime of x0? That must be equal to 1 by this initial condition. So our 2 by 2 matrix is 1, 0, 0, 1, right? Its determinant 1, which is not equal to 0, right? So by the theorem 4.3 that we've just proved, right? These two solutions, y sub 1 and y sub 2, are linearly independent on I, right? And the solutions of differential equation, right? Because this is a second order. And we now have two linearly independent solutions, right? That we call a fundamental solution of the equation, okay? So we are done, okay? So at least for little n is equal to, right? We confirm that there must be a fundamental set of solutions, right? Okay. For example, okay, in example 1, okay, we have handled before, we have seen that y sub 1 is equal to x, and y sub 2 is equal to x times the log of x. Okay. Both of them are solutions of this variable coefficients, linear, second order, homogeneous differential equation on the interval from 0 to infinity, right? Can you remind it, right? Let's compute the Wronskian, right? Okay. Wronskian of w of x1 and the y1 and the y2, right? What is it? This is the y1, which is x, right? And y2, that is x times the log of x, right? And its derivative is 1. Its derivative of x is the log x plus 1, right? Okay. Then how much is the determinant, right? X log of x plus x minus x log of x, that is x, right? This is never 0 on the interval from 0 to infinity, right? What does that mean, right? By the Wronskian test, okay, the two solutions, x and x times the log of x, is a fundamental set of solutions to given homogeneous second order differential equation on the interval from 0 to infinity, right? We can confirm it.